Hi students, welcome back to the session on free vibration. So in this video, I want to discuss about the effect of mass spring on natural frequency and the equivalent stiffness of a combination of springs. So coming to the first topic, that is effect of mass of a spring on a natural frequency. The previous video we already derived the natural frequency of a spring mass system where you are not considered the mass of the spring. If we consider the mass of the spring, what will be the effect it will be creating on the overall equation? So let us consider again the spring mass system as shown in the figure over here with the stiffness K, mass M, length of the spring as L. So now let us take X as a displacement of mass M and the velocity will be X dot. The velocity of the spring element, if I consider a spring element dy at a distance of y in the spring, the velocity of the spring element at a distance y from a fixed end may be written as, from the fixed end may be written as X dot into y by L. So where L is the total length of the spring. So the total kinetic energy of the spring element dy is given by, so of m value, that is the mass of the element, I'm going to take as rho. Rho is nothing but the density of the spring multiplied by the length, that is dy, multiplied by the velocity y by L into x dot whole square. So where rho is the mass of the spring per unit length. Therefore, the total kinetic energy of the system, including the mass, so I'm going to get as Ke is equals to of mx dot square plus, when I'm going to calculate the overall kinetic energy of a spring, I have to take the limit from 0 to L, that is the overall length. So I want to take in the integration by taking the limit as 0 to L. Equation becomes 0 to L of rho into dy multiplied by y by L into x dot whole square. So I want to differentiate this, so it becomes of mx dot square plus of constant I'm going to take, rho is a constant I'm going to take off. So dy I'm going to take as x dot square multiplied by 1 by L square. Again multiplied by the limits I'm going to take as y cube by 3. The limits will be 0 to L. So by applying the limits, that is upper limit over here L, and I'm going to get as L cube by 3. So L square and L cube get cancels, so I'm going to get as L by 3 left out. So I'm going to get overall equation as of mx dot square plus 1 by 6 rho L into x dot square. So ms is nothing but, I want to replace the length and the density with m into s, that is ms, that is the mass of the spring, ms as a constant. So I want to take as of mx dot square plus 1 by 6 ms x dot square. So now this is the total kinetic energy of the system when I want to consider the mass of the spring into consideration. So now coming on to the potential energy. So potential energy it will be in the spring. So potential energy will be equals to of kx square. So as per the energy method, so the total kinetic energy plus potential energy will be equal to, will be a constant. When I want to differentiate that, it will be equals to 0. So I want to find out the sum of the potential energy and the kinetic energy over here. So substituting the potential energy equation, that is of mx dot square plus 1 by 6 rho L x dot square plus the kinetic energy, that is the potential energy 1 by x square. I want to differentiate that with respect to time. I want to get as mx double dot plus ms x double dot divided by 3 plus kx equals to 0. So now I have to bring this equation into a standard part. So when I want to bring for the standard part, I want to take the common factor over here, that is x double dot by 3 I'm going to take as common, sorry x double dot I'm going to take as common. So I want to get as m plus ms divided by 3 into x double dot plus kx equals to 0. So I want to simplify this equation by dividing the complete equation by m plus ms by 3. I'm going to get as x double dot plus k divided by m plus ms divided by 3 multiplied by x equals to 0. Or I can write omega n is equals to root of k divided by m plus ms by 3. So that will be in terms of radians per second. If you want to get in hertz, so Fn is equals to 1 by 2 pi root of k divided by m plus ms divided by 3 in terms of hertz. So this is the equation you want to get when you want to consider the mass of the spring into consideration. So coming on to the equivalent spring constant, that is Ke value. So whenever it is found out by applying a load P or a moment M at the end of the spring system of a several spring and measuring the resultant total deflection. So now when I go for the equation, so K will be equals to load divided by the total deflection. So the springs can be arranged in a series parallel or combination of two also. You can see in this both sketches. So this is connected in a series and this is connected in a parallel, which is very similar to the resistors which you have studied in the first year when you go for electrical subject. So the resistors connected in a series are a parallel. So let us take the first condition when the springs are connected in a series. So when two or more springs are taken in a series, the spring constants are K1 and K2, then the load P. So if you are going to take the two springs over there, K1 and K2, the load P acts through the all of them and produce a deflection in the springs. So when you go for this, the deflection of each spring is given by load divided by the stiffness of the spring. So that is nothing but individual springs will have individual deflections. So that total deflection can be taken as delta 1 plus delta 2. So it goes on. So the deflection can be found out using the force applied divided by the stiffness. So delta 1 will be equal to P divided by K1. Delta 2 will be equals to P divided by K2. So substituting this equation, so I'm going to get delta is equals to, if I take the P common, so I'm going to get as 1 by K1 plus 1 by K2 plus 1 by K3. So delta can be replaced with P by delta, that is Ke overall, P by delta. So PP get cancels. I'm going to get delta as 1 divided by 1 by K1 plus 1 by K2. So R, I can write 1 by Ke, that is equivalent stiffness, is equals to 1 by K1 plus 1 by K2 plus 1 by K3 till it will be 1 by Kn. So this is the equation you're going to use to find the equivalent stiffness or equivalent stiffness constant for a series of springs connected to a system. So coming to second type, springs connected in a parallel. You can see over here the forces acting at and both the springs are connected in a parallel. So in this case, what will happen? The deflection. So it is assumed that load P produces equal deflection each of the parallel springs of the constant K1, K2. So when you want to pull the springs, when it is connected in a parallel, both the springs will go for a equal deflection, which will be equals to the overall deflection. That is nothing but delta 1 will be equals to delta 2 will be equals to delta. So delta 1 is nothing but the load by stiffness. So delta 1 is equals to P1 by K1. So I want to substitute that. So you're going to get as P1 by K1 is equals to P2 by K2. That will be equals to P by K. So I want to substitute that. So P is equals to P1 plus P2. That is P1 is nothing but delta into K. So I want to take delta. So it will be K1 plus K2. So when the springs are connected in a parallel, the equivalent stiffness Ke will be equals to K1 plus K2 plus K3. So it will be just a summation of the things. So just reviewing the things. So when you are going for the mass spring, so the mass ms will be added up, that is the mass of the spring will be added when you're going to consider the spring mass. So that is nothing but the rho into L. So rho is nothing but the density and the length L. So coming on to the next topic we discussed is equivalent spring system. That is nothing but when it is connected in a series, 1 by Ke will be equals to 1 by K1 plus 1 by K2 plus 1 by K3, so on. When it is connected in a parallel, Ke will be equals to K1 plus K2 plus K3. So next video we are going to discuss about free damped vibration.